Picture a supermassive black hole at the heart of a galaxy. It is easy to imagine a terrifying cosmic drain, a gravitational anchor so powerful it keeps billions of stars from flying off into deep space. But when astrophysicists run the numbers, that model falls apart. A central black hole typically accounts for only about 0.1% of its host galaxy's total mass. Its gravitational grip is localized. As you can see in this photograph of the Milky Way, the force keeping a galaxy together actually comes from the combined gravity of billions of stars, massive gas clouds, and invisible dark matter. This scatter plot charts black hole mass against the mass of the surrounding central bulge of stars, revealing a strict, direct proportion. Across almost every large galaxy observed, as the star cluster grows, the black hole scales right along with it. The fact that a black hole's mass remains so perfectly scaled to its galaxy, despite being too small to hold it together, suggests their relationship is not accidental. It points to a deep mechanical connection between the two that researchers are only just beginning to untangle. To understand how that connection is forged, we have to look back at the turbulent environment of the early universe. This was a volatile period filled with chaotic, massive primordial gas clouds. One theory for how galaxies formed in this chaos is the inside-out model. It suggests massive gas clouds collapsed directly to form a seed black hole first. Then the gravity of that seed pulled in surrounding matter, which eventually cooled and ignited to form the stars of a young galaxy. The alternate theory is the outside-in model. Here, dense clusters of early stars formed first. Over time, the massive stars crowded into the center collapsed into smaller black holes, quickly merging and consuming gas to forge a single supermassive giant. Regardless of which came first, the data shows they grew up together, linked as co-creations from their inception. A young galaxy is packed with heavy gas clumps and dense star clusters, moving chaotically in every direction. As these massive objects navigate the system, they experience a drag force called dynamical friction. When a heavy gas clump or star cluster plows through a sea of lighter gas and individual stars, it creates a wake, losing momentum in the process. Deprived of their forward momentum, these heavy masses, along with intermediate black holes, begin to spiral inward, sliding down the galactic gravity well. Once they reach the absolute bottom of that well, the exact geometric center of the young galaxy, they accumulate and merge, feeding a single, ever-growing monster. This process of gravitational sinking ensures the black hole is positioned at the epicenter, primed to dictate the behavior of the entire surrounding system. Sitting at that epicenter, the supermassive black hole acts as a massive sink. As it pulls in surrounding gas, the material swirls into a superheated ring known as an accretion disk, clearly visible as the bright orange halo in this photograph of M87's black hole. The sheer friction inside that disk heats the gas to millions of degrees. This triggers a phase called an active galactic nucleus, or AGN, where the black hole shoots massive jets of plasma outward into space. We observe these ejections directly. This ultraviolet imaging captures an intense linear jet of radiation slicing outward from the nucleus. Acting like cosmic blowtorches, they punch through the host galaxy to disrupt and superheat the remaining cold gas scattered throughout the system. Consuming matter generates the energy needed to physically reshape the entire galactic environment. This creates a regulatory feedback loop. First, cold gas falls into the center. The black hole feeds and grows, which eventually causes it to fire those powerful AGN jets. Because new stars require cold gas to condense and form, those superheated blasts effectively shut off new star production across the galaxy. But with the cold gas heated or blown away, the black hole simultaneously cuts off its own fuel supply. With nothing left to consume, the black hole's growth stalls. This mechanism functions as a safety valve. By regulating the surrounding gas temperature, the black hole prevents the galaxy from churning out stars until it exhausts itself or tears its structure apart. By balancing the heat, large galaxies and their central black holes maintain a permanent equilibrium. It proves that on a galactic scale, destruction and creation are just two halves of the same cosmic cycle.